We've learned that reaction rates generally increase when we have increasing reactant concentrations, right? The rate law usually has at least one of these reactant concentrations in it, and the higher the initial concentration, the faster the rate. A reversible reaction can proceed in both the forward and the reverse directions. As the reaction goes in the forward direction, the reactant concentrations go down, and so the rate of the forward reaction gets slower. As the reaction goes forward, the concentrations of the products become larger, and that causes the rate of the reverse reaction to increase. So as the reaction goes on, the rate of the forward reaction gets slower and the rate of the reverse reaction gets faster until at some point they become the same rate. They are equal to each other. So here we have an illustration of this. Here's time passing. That could be seconds or minutes. Doesn't really matter. And we're looking at this reaction between hydrogen and iodine to form high. So in the beginning, we have 0 of the product, and we have some concentration of each of the reactants. As the reaction goes in the forward direction, these reactant concentrations go down, and the product concentration goes up. As this is going up, the reverse reaction is going faster. As these go down, the forward reaction is going slower. At the point we call equilibrium, there is no net change in the concentration of the reactants and products. It's called a dynamic equilibrium, though, because the forward and reverse reactions are still going on. It's just that they're going on at the same rate, and so the overall concentration isn't changing. I think I mentioned an airport analogy. Busy airport in the middle of the day, and let's say there's 5,000 people in the airport. An hour later, there's about 5,000 people in the airport. Are they the same 5,000 people? Probably not. Because some people left on airplanes, and some people came on airplanes. And some people came in cars to get on the airplanes, and some people went out and left in the cars, right? So it's going both ways, but overall, nothing seems to be changing. That's dynamic equilibrium. So dynamic equilibrium is the condition in which the rate of the forward reaction equals the rate of the reverse reaction. They're both still occurring. The concentrations of reactants and products aren't changing anymore, but this is important. They are also not equal to each other. A dynamic equilibrium does not mean that this reaction is balanced at the halfway point. It just means that it's come to a point of balance and the concentrations aren't changing. Those relative concentrations are going to depend on the value of the equilibrium constant. We could have the product concentrations being very, very high and the reactants being low, or vice versa, or we could have them being equal or anywhere in between. So here's an analogy, and there was one edition of the book in which they didn't call this country A and country B. They called it Middle Earth and Narnia, and I just like that so much better. So this is Middle Earth. And this is Narnia. Why not just, mix up our fantasy worlds? So, migration or immigration works this way as well. So initially, there's a lot of people living in Middle Earth, and there are very few people living in Narnia. So some of these people from Middle Earth say, well, the grass looks pretty green over there, and so they move to Narnia. When there's no one living over here, can we have anyone moving back to Middle Earth? No, we can't, because there's nobody to come back, right? So we have this net movement from this side to the other side. So this is like the reactants and the products. As more and more people move to Narnia, now we've got fewer people in Middle Earth. It's maybe not as crowded as it was before. And people that came over here are like, well, yeah, this is nice, but it's not really all it was cracked up to be. I think I'd rather go back over here. And so as more and more people move to Narnia, then the rate of people moving from Narnia to Middle Earth is going to increase. And at some point, it will come to an equilibrium where you have equal movement in both directions. Any questions? Okay, which statement does not generally apply to a chemical reaction in dynamic equilibrium? The rates of the forward and reverse reactions are equal. Is that true? Yeah, that's the definition of dynamic equilibrium. The rates of the forward and reverse reactions are equal. The concentrations of the reactants and products are constant. Yeah. The concentrations of the reactants and products are equal. No, they're not. So that's the one that does not generally apply. So let's go back to Narnia and Middle Earth. When things settle down here, are we necessarily going to have an equal number of people in Middle Earth and Narnia? No. What if Narnia is just not as great as it looked, and maybe there's some places that are really great to live, but other places are just like way too hot, like Fresno, and so it's maybe not as desirable to live here as it is in Middle Earth. If this is a nicer place to live, if there's more fun things to do, if there's more resources, more people are going to choose to live over here, right? I think we kind of understand. Chapter 16, Chemical Equilibrium. Every system in chemical equilibrium under the influence of a change of any one of the factors of equilibrium undergoes a transformation that produces a change in the opposite direction of the factor in question. That's a quote from Henri Le Chatelier, who is the person that Le Chatelier's principle is named after. And he lived a long time ago. So we mentioned equilibrium on Monday when we were talking about reaction mechanisms. Now we're going to learn a lot more about it. So the speed of a reaction is determined by kinetics. And that's what we've spent the last 2.5 weeks talking about, is kinetics. How fast does the reaction go? The extent of a reaction is governed by thermodynamics. So the equilibrium constant, K, capital K, is a measurable quantity that quantifies how far a reaction goes. There are very few absolutes. And so in Chem 1A, we kind of assumed that all of one of the reactants is going to get used up. The limiting reactant is going to get all used up and make products, and that's how everything works. That's not really true. Most reactions do not go to completion. There's still some reactant left. And so the equilibrium constant helps us to know the extent of the reaction, how far it goes. So this equilibrium constant K, if that is large, it's going to favor the products. So if you have a large equilibrium constant, you're going to have a lot of products. If you have a small equilibrium constant, that means that you're going to mostly have reactants. We'll learn more about the reasons for the size of the equilibrium constant in chapter 19, but that's for later. Okay, so let's look at the relationship between hemoglobin and oxygen in terms of equilibrium. As you probably know, red blood cells contain a protein called hemoglobin, and this is an illustration of that. This very large protein and so it's just abbreviated HB. Hemoglobin reacts with oxygen to form this complex. And when we write this equation, we have a double-headed arrow here, which indicates that the reaction can go in both directions. This is a chemical equilibrium. The concentrations of the reactants and the products are described by the equilibrium constant that we're going to learn about. And Le Chatelier's principle illustrates that equilibrium systems respond to changes in ways that maintain the equilibrium. So a chemical equilibrium is trying to maintain the status quo. It's like, I like things the way they are right now. You force a change on me, I'm going to do what I can to make things the way they were. Personally, I can kind of relate to this because I only like change if it's my idea, right? If somebody else imposes it on me, I'm going to resist. So hemoglobin will bind with oxygen, and it transports the oxygen from your lungs all over your body, right? So in your lungs, there's a lot of oxygen, relatively speaking. And so because there's a lot of this reactant, the reaction shifts to the right, and the hemoglobin will bond with the oxygen. As the blood with the hemoglobin goes through your muscles and organs and other tissues, the oxygen level drops because the tissues are waiting for the blood to bring it more oxygen. So if this oxygen level is lower, then the equilibrium shifts to the left, and the hemoglobin that is carrying oxygen gives it up. Let's go with it. And so it really is a remarkable system where in the lungs where there's lots of oxygen, the hemoglobin will pick up the oxygen, and as it goes through places where there is less oxygen present, it lets go of it and provides oxygen to those tissues. So that's how it works in your blood. What about an unborn baby? Unborn babies have lungs, but they're not breathing air, right? They're being nourished through the mother, but there's no direct connection between their blood. So how does this work? Well, fetal hemoglobin, which is HbF, is slightly different than regular hemoglobin. It has a larger equilibrium constant, and so it's going to load the oxygen at lower concentrations. So we have the maternal blood and the fetal blood in very close proximity to each other. And so the fetal hemoglobin in the baby's blood will get oxygen from the mother's hemoglobin, even under those lower oxygen conditions. It will still load. Normal hemoglobin here would not pick up the oxygen that the regular hemoglobin is letting go, right? But because this is a special kind of hemoglobin, it will pick up that oxygen and can transport that to the baby. This is not something that I'm going to test you on, but it's just an illustration of the application of equilibrium. Does anybody have any questions?